Now I would like to discuss the activating groups for the polysubstitution of benzenes. And the easiest to analyze is actually substitution that exhibit just a plus I effect. Substitutions that show this effect are, for example, alkyl chains. They have no lone pairs that can somehow interact with the p or pi electron density of the benzene ring. So the only thing that they do is they have additional electron density present at the, for example, carbon atom attached directly at the benzene ring. So they slightly push along the sigma bond a little bit of electron density into the benzene ring. And this makes the benzene core, of course, a little bit more activated for a second substitution reaction. We have seen this as an example during the Friedel-Crafts alkylation reactions, where actually the second and subsequent additions of an alkyl chain were a little bit more favored than to the unactivated benzene core. Of course, the same goes for substituents that have a minus I effect that just draw a little bit of electron density out of the benzene ring. They basically behave the same. So I effect is important to analyzing this, but it's not like the main factor that contributes towards the activation of a benzene core. The other thing that's really important is the so-called mesomeric effect, often also abbreviated to M effect. And you can have, as in the same way you can have a plus or minus I effect, you can also have a plus or minus M effect. And in this example, we see the influence of an amino group on the distance here, on the benzene ring here. The amino group is comprised of a nitrogen atom and 2 hydrogen atoms. So it's basically the organic equivalent of ammonia. And the nitrogen has a lone pair attached on it. And this lone pair can now interact with the pi electron density of the benzene core. And it can happen in such a way that the pi electron density gets moved in here during this intermediary carbocationic stage, and then this positive charge gets located on the nitrogen atom. And this stabilizes actually the positive charge because there's now one more resonance structure to stabilize. Initially, we have seen that it's only the positive charge could only be located in ortho position relative to the point of attack of the electrophile or in para position. But now there's like this amino group also helps in delocalizing this positive charge, and this overall stabilizes the intermediate. So the amino group now works in this case as a strongly activating ligand for this second substitution reaction at the benzene core. You can also see the row or the row of these plus M substituents here. Amino groups actually have a very strong M effect. They are willingly pushing the electron density via this M effect into the benzene core. Oxygen atoms here in the form of the phenol ligand or the hydroxyl group, and then we call this a phenol. They are also they also have a strong M effect, but the oxygen is slightly more electronegative than the nitrogen. So the oxygen is a little bit more hesitant, I would say, to donate the electron density. In this case here, for the carboxylic acid-based group here, the M effect is actually even worse than for the hydroxyl group. And that is because we now have a strong minus I effect, and then also this minus M effect of this adjacent carbonyl group here. So this also pulls on the electron density that we would like to, of course, donate into the benzene ring. But because the carbonyl group also is part of this mesomeric structure, it also withdraws a little bit of this electron density. This is even worse. And then we have carbon-based M substituents, for example, another benzene ring. We also call that a phenyl substituent. And this is also possible to locate part of its electron density into the original benzene ring, but this is also not the best way of doing this. So overall, you would like to have these plus M substituents at your benzene ring to activate your benzene ring for a subsequent electrophilic reaction.